Helmholtz free energy, often denoted by the letter A, is a thermodynamic potential that measures useful work. It measures the work obtainable from a closed system. The closed system must be at constant pressure and volume. So mathematically we can express Helmholtz free energy as A is equal to U minus T S, where A is the Helmholtz free energy, U is the internal energy of the system, T is the absolute temperature, and S is the entropy of the system. And this always represents maximum amount of work obtainable from a closed system. And the work here excludes pressure volume work. And Helmholtz free energy is useful in studying systems that are closed wherein the volume is fixed. For example, chemical reactions in rigid containers. So the Helmholtz free energy can be applied in electrochemical systems, gas reactions, solid state systems. In the case of gas reactions, it must be in closed containers. So now to understand the relation to spontaneity, so if the change in Helmholtz free energy represented as delta A is less than 0, then the reaction is spontaneous. If the change in Helmholtz free energy is equal to 0, then the system is at equilibrium. If the change in Helmholtz free energy is greater than 0, so the meaning is the process is non spontaneous. Let's study an example of combustion of hydrogen in a rigid container. So, as we can see here, the system is a rigid sealed container that holds a stoichiometric mixture of hydrogen and oxygen, and the system is at constant volume because it is a rigid container, so the volume doesn't change, and the temperature is also a constant. So, there is no pressure volume work happening here. So in this case, the expansion work is 0. So this is going to give the maximum useful work from the reaction, that is combustion here. So it is going to give maximum work which is non-pressure volume work. To understand the significance of Helmholtz free energy as work function, we are going to see a derivation. So Helmholtz free energy is defined as A is equal to U minus T S. So if we take change in state at constant temperature, so this expression can be written as del A is equal to change in internal energy minus temperature and change in entropy. So let's take this equation as equation 1. If we take reversible heat transfer, from the definition of entropy for a reversible process, so we can write the reversible heat transfer as Q is the reversible heat transfer with a subscript REV, which is going to be equal to temperature into entropy. And we are going to call this equation as equation 2. So when we substitute the equation 2 into equation 1, we get the change in Helmholtz free energy is equal to change in internal energy minus the heat involved in reversible heat transfer. And we are going to call this equation as equation 3. So we are going to apply the first law of thermodynamics. So the first law of thermodynamics states that change in internal energy del U is equal to heat minus work done. So for a reversible process, if we rewrite this, so we can rewrite it as del U is equal to heat transferred in a reversible process minus work involved in a reversible process. So we are going to call this equation as equation 4. So now we are going to substitute the equation 4 in 3. This is the equation 3, that is change in Helmholtz free energy is equal to del U minus heat involved in reversible heat transfer. So substituting equation 4 into 3, we are going to get del A is equal to heat minus work of the reversible process minus heat involved in the reversible heat transfer. So the heat and the heat get cancelled out, and what we get finally is minus reversible work done. So we can say the final relation is going to be, so change in Helmholtz free energy is equal to minus reversible work, or we can also write it as the work done in the reversible process. So this work is non-pressure volume work, which is going to be equal to the negative change in Helmholtz free energy.